kind of remind you of is we had an overall setting where there were three things that both of these distributions had in common. The first thing was that we had to have a situation where it was success or fail. So it had to be binary, and that was true also for binomial. We also had to, hand in hand, have trials that were independent, and because they were independent, the probability of success had to remain consistent. Basically meaning it can't be a situation like a deck of cards where if I pull out a hearts, now my probability of hearts has gone lower. So these three things together were all what composed a Bernoulli trial. And then it kind of separates into two different types of categories. The first thing that we discussed before we left for Thanksgiving break was a binomial distribution. Now, binomial, the specific kind of attribute to that was that we had a fixed number of trials. So you are going to go in, you are going to select or shoot, I think basketball is one of the examples today. You're going to shoot 10 basketballs and see how many of the shots you can make. They would tell you how many things you are doing. So binomial is there is an end point. There is a point where you are going to stop doing this random event. For geometric, it's slightly different. With geometric, you are specifically interested in your trials until the first success. So when I'm doing trials until the first success, I don't necessarily have an end point. It could happen on the first trial. It could happen on the 10th trial. It could happen on the 100th, 1,000, 1,000,000th. Realistically, it's probably going to happen. It's not going to take 2 million times to do something. But with geometric in and of itself, it could. So whenever we have a geometric distribution, there is no end. So it technically goes on forever and ever and ever. And so just a little tie-in to kind of things we've talked about before. If this were a distribution, and if I were to kind of plot this out as a histogram, it would be skewed to the right because I would have possibilities all the way out to like the millionth, 2 millionth, 10 million thousandth trial. So it's going to keep going forever and ever and ever. So anytime you look at a question and they say first, the first time you do this, it is always geometric. Sometimes they will nest geometric questions into binomial questions. So they'll tell you, you're going to shoot the basketball 10 times, but they may ask you later on, what's the probability of making your shot on the first try? Anytime you see first, that is going to supersede any other type of question. So it could be a binomial overall setting, but if you see first, it is going to be geometric. Now, the nice thing about kind of going in and doing geometric is it's very, very similar to binomial. One thing that often gets asked is they want you to make a probability distribution. So remember, if you ever see probability distribution, create a probability distribution, all they want is a table. So the table is going to have two things. It's going to have your outcomes, and it's going to have your probabilities. So this kind of ties into what we did in like 5.5 when we were making these probability distributions and finding the expected values and things like that. So when it comes to a geometric distribution, if I'm trying to get the first success, that means every time I start one of these tables, it always must start with 1. So in like kind of comparing this again to binomial, if I were in a binomial setting, it will always start with 0. Always starts. Because if I'm shooting a basketball 10 times, there's a chance I miss all 10 of them. And that would be having an outcome of 0 baskets made. So anytime you are starting, and this could be helpful if they give you a table and you're like, okay, am I supposed to be doing binomial or geometric? If you look at the first term and it's 0, it's binomial. If you look at the first term and it's 1, it's potentially geometric. The one thing about these also is because there is no end in sight, we have to write these tables with the intention that the last cell typically is going to cover everything else. So it's not just 4. Sometimes they only ask you for 4 and that's what you want. But if they're saying to write the complete probability distribution, then that last cell is going to contain every single remaining probability. So just to kind of go in and tie in some more from 5.5 and 5.6. We have a situation where they're telling us, let X be the number of trials until you roll a 6. This is a 6-sided die. So my probability of success is going to be 1/6, because there's a 1 out of 6 chance that I roll a 6 on a 6-sided die. Now, these outcomes represent the trial where you get your success. So when I see 1, that means that I got my success on the first trial. Well, the probability of that happening is 1/6, which we can put into a decimal because we're going to need it later. So I have my fraction, I have my decimal. Now, something that we did in 5.5 and 5.6 was we talked about how if you want multiple things to happen together, that is when you're using the multiplication rule. So if I'm looking at number 2, that means that my success occurred on the second trial. So that means the first time I rolled the dice, I did not get a 6. So there's a 5 out of 6 chance of me not getting the 6 at all. And then I come in and I roll again, the second trial, and I get a 1 out of 6. And so that probability is the chance I have of getting it on the second trial. And so if I put that into decimal, 1389. Now, it kind of continues on for for number 3. That is getting 2 failures. So missing, and then on the third trial, getting your success. So you can write this as 2 separate fractions if you wanted, but you also can just raise that first fraction to the power of how many failures would be occurring. So in this case, I failed 2 times, and then I got success on the third one. And so that's going to be 0.1157. And then when we get to the last one, 4 or more. So everything other than 1, 2, and 3. And usually the easiest way to do this, especially for geometric, because there's no ends in sight, like you can't find all of the individual values, it could technically take you 1,000 tries before you get a 6. Realistically, probably not going to happen, but it could. So what we do if we want to find anything other than the ones that we have, we talked about how the easiest way to do that is to just subtract what you know from 1. So we know the trial 1. We know the trial 2. We know trial 3. So I can subtract all of those from each other, or add them all together and subtract it from 1. And the probability that it could be 4 or more is 0.5787. So this would be my probability values for this probability distribution. Now, it doesn't always end at 4. They may ask you for 4, 5, 6, and then say 7 plus. They may just ask you for 4, 5, and 6 and not have a complete probability distribution table. But in total, if you're doing every single outcome, it should always still add to 100, to 1 value total. So again, don't overcomplicate when they ask you for a probability distribution. It is simply just create a table listing the probabilities and listing the outcomes. Now, what we kind of just did with that multiplication rule is essentially the formula for geometric. The geometric probability formula, this is one that you do not have to memorize. This is on the formula chart. We will kind of talk about that at the very end on the formula chart. You have your probability of success on the first whatever trial you're interested in. All of these, kind of like everything we've done, will require a probability statement. And then what you do is you're going to have as many failures as you need to make it to that specific number you're interested in. So 1 minus p is the probability of failure, and then you're just raising that to whatever number you're interested in minus 1. So if I want it to happen on the 10th trial, this exponent would be 9. If I wanted it to happen on the 8th trial, this would be 7. If I wanted it to be the 100th trial, this would be 99. So it's just whatever number you're interested in minus 1. And then at the very end, you're going to have a probability of success. Because like in my table, all of the probabilities that I calculated ended with me having a success at the very end. And it's only one. It's not something where if you get a question and they say, what's the probability of getting 2 successes or rolling 2 6s in a row or in a situation? That kind of turns to binomial. They would have to give you a number of trials. You can't necessarily use geometric to go in and say, until I roll 2 2s in a row. So it's always going to be interested in one first success. So let's go in and let's try this with the formula, and then we'll try it with the calculator. I will kind of show you my expectation for what should be on an FRQ question. We're in the same situation. We're still going to roll a 6-sided fair die until we get a 6. So that means the probability of success is still 1 over 6. Same thing that we were just dealing with. And so what is the probability that you get your first 6 on the 5th roll? So if it's happening on the 5th roll, that means that there was 4 failures before we got the success. So when I write out my probability statement, I'm going to have the probability that x is equal to 5. And that 5 just represents when are you getting the success, 5th roll. And so in order to kind of set this up, I know that the probability of failure is 1 minus p. So that is going to be my 5 over 6. These are all of the other numbers that are on the dice that I don't want. And so if it's happening on the 5th roll, that means I have to have 4 failures happen before I get the success. So 5 over 6 to the power of 4. And then I'm going to have 1 over 6. So 4 failures and then a success. And this is something that does not necessarily require any calculator functions. This goes directly into your calculator exactly as is. And when we plug this in our calculator, we should be getting 0.0804. And I will say, when it comes to geometric, a lot of people, if it's just an equal to, they will kind of lean towards just doing the formula because it's kind of something we've been doing since we started Unit 4 and probability overall. And they kind of lean towards that more than just doing the calculator function, which we will still discuss, but sometimes it's a little less writing than using the calculator. So if you were to answer this question with the formula, this is what you would have. Now, part B, what is the probability that you get your first 6 within 3 rolls? So what this means is it could happen on the first roll, it could happen on the second roll, it could happen on the 3rd roll, one of those 3. And so what I can do, I can write this as x is less than or equal to 3. And what I'm actually finding is the probability that x is equal to 1 plus the probability that x is equal to 2 plus the probability that x is equal to 3. Now, I specifically picked this setup because we've already found these values. If you look on the front page in the table that we made at the very, very beginning, we have all of these probabilities calculated. We have 1 over 6. We have 5 over 6 times 1 over 6. We have 5 over 6 squared times 1 over 6. So we found each of these values on the front of these notes. So I'm just going to take the decimals that we got, and I'll make a note that we have this from the front table. But I'm just going to take all of the decimals that I found, and I know we can kind of work in complements if we really wanted to with what we currently have. And I'm going to add them together, and I'm just going to say probabilities came from table on first page. If you go back and you look at your notes and you're like, where did we even get these numbers from? That's where they came from. Go in, add all of these together, and we get 0.4213. And very similar to when we'd use like tree diagrams and things like that, if you have found values in a previous section of your question on an FRQ, you don't necessarily have to rework it. Now, yes, we could have gone in and rewrote all of these out and found them separately again, but if it's on another part of your question, you don't have to do it. So a lot of what happens is they take that value that you found and they kind of carry it through the remainder of the question because they don't want to have to like double dock you. Say, for instance, you missed one of these probabilities. You messed it up. You did 4 over 6 instead of 5 out of 6. But every other problem after that you did correctly using the incorrect values, they will still give you credit for the stuff that you used because you thought it was correct. So this is why we say if you found something already, use it. Because most of the time, at least in probability, we find that they try to build you up so that you're just not doing 10 separate calculations just all on different topics. The last one, what is the probability that it takes at least 4 rolls? Now, this is a value that we actually have in the table. So at least 4 means that we are including 4 in our calculation. If this had said more than 4, so just to kind of point out the difference, more than 4, I would be writing the probability that x is greater than 4. So the hardest part that I kind of see when I grade these tests is people trying to get the inequalities correct. Do I include it? Do I not? And that's why some of those math lab questions are written in almost identical language with slight variations. So you can kind of see how these wordings can look different. If you're kind of stuck on that, the binomial notes that we did kind of covers most of the wording for any of these types of questions. Now, for probability that x is greater than or equal to 4, the easiest way to do this, and I know we have it in the table, but I'm going to work through it like I don't, I could go in and I could use complements. So if I want 4 or more, because, again, geometrics don't really have an ending point, I have to work with the complement of that probability. And if you ever get stuck, my suggestion, and I know it seems kind of silly, I go in and I write out a little number line. So 3, 4, 5. And I go and I circle, what do I actually want? I want 4 or more. So I always kind of see this is the values that I'm interested in. And then I look at, okay, well, what's the last excluded value? And in this case, the last value that I'm not including is 3. Yes, in most cases, you can just subtract from 1, or you can just subtract 1 from your number. However, if we look at that more than 4 question, if I wanted to do more than 4, that's not actually including 4. That means I want 5 or more. So if I were to write this one, it would actually be 1 minus the probability that x is less than or equal to 4. So be careful on those questions where you're not including the value, because that is not a situation where you end up subtracting 1. That number actually is the same even in the complement. It's just in the complement it's included and not excluded. So just be a little careful there. Now we've already found this value, 1 minus the probability, and in part B we said it was 4 to 1, 3. And this should match our value from the table that we got at the very end, 0.5787. And if you need to, maybe draw like a, this is separate. That has, it's kind of like the question, but doesn't have anything to do with the question. Okay, so this is if you wanted to do it by hand. If it's an equal to, I will sometimes just do it by hand because it's a little easier. Anytime I have to do a less than or a greater than, I'm most likely using the calculator because I don't want to have to calculate a bunch of different probabilities. So the nice thing about the calculator, we have used the binomial distribution just to kind of rope that back in so we can kind of remember. Binomial, there were two functions. There was binom PDF and there was binom CDF. Both of these functions are going to work exactly the same as they do in geometric. PDF was always if it was an equal to, and CDF was a less than or equal to. So just in the exact same way, we have a geomet PDF, which is going to be for anything equal to a number, and we have a geomet CDF for anything that is less than or equal to a number. Now, the only tricky part about your calculator is your calculator can only do less than or equal to. So anytime we have to do greater than, we have to use complements. So make sure that you kind of keep that in mind. Must use a complement. 1 minus. Now, with the PDF and CDF, the characteristics are the same for binomial and geometric. The one change that's going to kind of occur when you open up a binomial function, it asks you three things. It asks for trials, it asks for probability, and it asks for x value. And what you'll notice is when we start to open geometric today, it asks you for the probability of success, and then it asks you for the x value. I know it said k, the formula a couple years ago used to have k in it, and we changed it, and I just forgot to change the notes. So again, usually the difficult part for people is deciding between, is this binomial, is this geometric? If you cannot go in and answer the question of how many trials do I have, it's probably not binomial, because you have to have that information for your calculator to even do anything with the function. So if you don't have a set number of trials, you are not doing binomial. When you open up geometric, it only asks you two things. What's the probability of success? What number do you want the success to be? Now, if it was worded that way, it'd be so much easier, but it's going to say x value, and that's just what number of success do you want. Both of these are found in the same menu. If we go to second vars, you'll see binom PDF, binom CDF, and then you'll see geometric PDF, geometric CDF. So you're not going to different places in the calculator. You're just making the decision of first, is it binomial, is it geometric? And then you're making the decision of, is it a PDF or is it a CDF? So it's kind of like that's how your thought process should be working. So for our example with the calculator, it says let x be the number of baskets until he makes his first free throw. The player has an 82% chance of making a random free throw. So that means his probability of success is 0.82. All probabilities have to be in decimal form. So part A, what is the probability he makes his first basket on his 5th attempt? I'm going to go in, probability that X is equal to 5. Now, for the calculator, just like with binomial, there's a couple of requirements that you have to get full credit. You need to list the function. So it will require you saying either geometric, geomet, or binomial, binom, as a part of it. You can't just say PDF, CDF, and then hope like, oh, maybe she's not going to read it. It has to state which distribution you're using. In this case, because it's an equal to, this is a geomet PDF. So both parts of the calculator function have to be there. And then you just go in and you have to state the probability of success, 0.82, and you have to state the X value, which in this case is 5. That is when I want the first success to occur. A big thing that people lose credit for on the AP exam, College Board is really nitpicky. It's a weird thing that they have you do, but you have to label P and X value. It is not something where you can just come in and say Geomet PDF 0.825. They want you to label them with what you are seeing in the calculator. You don't have to tell them, I went to second VARS, I went to letter E, I went to Geomet PDF. You just need to have the calculator function, the numbers, and the labels. That is what's going to get you full credit on the exam. So what I'm going to do, I'm going to open up my calculator. I have second VARS. I'm going to go, I usually go up because it's a little faster instead of down. I'm going to go up. I'm going to go to Geomet PDF. And yours should take you to a whole new window. It should ask you for prompts. You're going to type in 0.82 for P, and we're going to type in 5 for the X value, and then we're going to hit enter. Now, one thing to be really careful about is whenever you get these numbers that look like they're whole numbers, they're not really whole numbers. At the very end, you see e to the negative 4. That means I'm moving my decimal to the left 4 times. So when I come in and I actually write this out as a decimal, I'm going to have 0.000 and then 9. Even when it tells me something more than 4, I will usually try to take it to at least one significant digit. If it's like e to the negative 20, I'm going to say like approximately 0, because you don't have to write 19 zeros and then just have a 1. It's basically 0 at that point. So anything like 4, 5, 6, I will take it to a significant digit. Anything bigger than that really kind of just becomes 0 either way. So this is what you need for full credit on your test. Now for the next question, what is the probability it takes less than 4 attempts to make his basket? Now when we say less than 4, probability that X is less than 4, that isn't including 4. So this is one of those situations where when I go in to find the answer and I use the complement, I'm not actually subtracting 1. So this is actually 1 minus the probability is, oh, never mind, wrong thing. It's not a complement. It is just a less than. I got ahead of myself. It takes less than 4 attempts means we're not including 4. So when I go in to write this out, anytime it's a less than, we are going in and we are using a CDF. Another way that you also could have written this particular problem is you could have written this as X is less than or equal to 3. Because if I want everything that's going to be less than 4, that means 4 I'm not including in my actual calculation. So I'm going to go in and I'm going to use a geomet. And I will say I'd be careful once you start using both at the same time, because you will have like both of them on your test. Just making sure that you're actually writing the calculator function. When I was teaching this yesterday, I sure did write binomial a couple times and had to correct myself. So just make sure that you read through and you are double checking your work. So I have Geomet CDF. My probability of success is 0.82. and then my X value. In this case, whenever you're using CDF, it's always what is the last value that you want to include. And the last value that I want to include is going to be 3. And if you need to make yourself a little note, this is the last included value. And this is going to go into your calculator exactly the same way as a GeoMet PDF. It's in the same menu. It asks the same questions. So I'm going to just switch over really quick. We have second, vars, I go up. There's GeoMet CDF, 0.82. And the last included value I want is 3. And then I hit enter, and I get a probability of 9942. Same kind of rounding rules apply as to things we've done before, 0.9942. I don't necessarily care if you leave it as a decimal or, and the reason why we go to 4 decimal places, if you wanted to convert it to a percentage, it's 99.42%. So there's a 99% chance that he can make it in his, or it takes less than 4 attempts to make his first basket. Okay, now let's do a complement. So what is the probability it takes at least 3 attempts to make his first basket? So that means I want the probability that X is going to be greater than or equal to 3. Because when we say at least 3, that means we are including 3. And so the complement of this is a situation where we are going to actually subtract from that value. So I'm going to have 1 minus the probability X is less than or equal to 2. And again, if you're like, how do I know that? Write a little number line. I go in and I do 2, 3, 4, and I go in and I circle, okay, I want 3 or more, so my last excluded value is 2. So I just make a quick visual representation showing me what do I actually have to find. Now, anytime you do this, if I had calculated X is less than or equal to 2 anywhere else in the question, I could just use that. So that's what I mean when I say pay attention to some of the parts that you've done, because sometimes you've done the work. I didn't actually find this value, so I have to go in and do, not a binom, see, I did it again, a GeoMet CDF, where my probability is 0.82, and my X value that I'm interested in is going to be 2. So that's going to be my last included X value. I will say this, the biggest mistake we see on complement questions, everything gets set up correctly. You find GeoMet and then you forget to subtract it from 1. So what I usually do when I take this to my calculator, before I even go to the GeoMet window, I do 1 minus and then I do second vars, just so I make sure the number that I'm getting out of the calculator, I know I've already subtracted it from 1. So I do second vars, I go to GeoMet CDF, 0.82, and then my X value is 2. And then I get 0.0324. And I can almost guarantee if this were a multiple choice question, they would have an answer choice where it would just be the GeoMet calculation. And so that would be something where they tried to trick you, because most of us, when we're like, oh, I did all this work and now my answer is one of the answer choices, it must be right, we just pick it and move on and don't actually double check it. Be very careful in those situations where it's multiple choice, because it could happen. Okay, now the last kind of thing we're going to talk calculator-wise with different types of questions they could ask you. Sometimes they kind of switch it up a little bit. So in this case, for part D, it says, what is the probability he will make 6 baskets in a row before he misses? And making 6 baskets in a row, that probability of success was 0.82. But before, we consider that to be our success, and then our everything else that happened before was the fail. But they're kind of switching the direction of what they actually want. This is changing the random variable itself. So I'm going to go ahead and use random variable y just to kind of change it up because X technically covers making the basket. I'm going to say number of basket attempts before first miss. We'll do until. I don't want to say before. Make my wording a little bit nicer. Because before, people could argue it's like all of the numbers before. We want it to be y represents, I want him to miss on this shot. Okay, and so if I wanted to do a probability of success in this setting, it's not going to be 0.82, it's going to be 1 minus 0.82. Because if he has an 82% chance of making it, if we want him to miss, that means he has a 0.18% chance of missing. So I could go in and I could go and find the probability that y is, so if he makes 6 and then he misses, that means y is occurring on the 7th trial. Now, in this case, a lot of people, again, favorably are going to just say, okay, well, I'm just going to take 0.82 to the power of 6, and then I'm going to take 0.18, and I'm going to get my number. Wonderful, amazing. If it's an equal to, generally I favor the formula over the calculator. You still can do this in your calculator. You still can do a Geomet PDF where your probability is now 0.18, and I know it says X value. We're still going to call it X value because that's the calculator function. If you want it to actually say Y value, you can. X value would be 7. It still, no matter which way you pick, is going to give you the same exact answer. You're going to get 0.0547. And I know my audience, and usually people are trying to write as little as they possibly can. And that's why when it comes to geometric, people favor the formula because it looks like a lot less writing than doing the calculator function. If you are using the calculator function, you have to write every single piece. It is not just something where you can say like GP 0.187 and expect to get full credit. That is not going to get you anything. College Board is going to throw it out and they're going to say doesn't count. You have to do this. I'm not writing this just for me to be nitpicky. I'm writing it because this is what College Board requires on the AP exam. This is the minimum, the bare minimum. Okay, let's go in. Let's talk our last little bit, mean and standard deviation. Just a reminder, again, because I want to kind of loop back in binomial since it has been a week and a half-ish since we talked about it, almost 2. If I want to find the mean for a binomial, it is going to be n times p, standard deviation of a binomial, square root np 1 minus p. The only reason I point this out is, again, if you are having a tough time deciding between binomial and geometric, all of the binomial things that you do require a number of trials. So if I see n, I know I have to have some situation where my number is listed out. And if it's not binomial. So that's when you jump to geometric. Now these formulas also on the formula chart, again, we'll kind of talk about it in a second. We have our mean. Sometimes the mean is referred to as the expected value. If you see the word expect, you're finding a mean. And then you have your standard deviation. And this is the one where you're usually going to see typically varies. So sometimes they're kind and they just tell you find the mean, find the standard deviation. And sometimes the language of the question itself is going to revolve around expected value and typically varies. So in our example, We have Drew decides to place a $10 bet on number 3 for a roulette wheel until he wins. On any spin, Drew has a 1 out of 38 chance that the ball will land in number 3. And we're going to let X be the number of spins until the first win. So this means my probability of success is 1 out of 38 because he only has one number. That's what he's betting on. That's what he has. How many spins do you expect it to take until Drew wins? So if you see the word expect, that means you are finding a mean. And then what does this typically vary by? That basically just means we're doing a standard deviation. So I'm going to take these two formulas and I'm going to plug in 1 over 38. So I'm going to have my mu of x is equal to 1 over 38, which turns into 38 spins if you keep change flip from algebra or plug it into your calculator. So mu of x, 38 spins. Anytime you report a mean or a standard deviation, you have to have units. Standard deviation, square root of 1 minus 1 over 38 all over 1 over 38. And you can go in and convert this to a decimal and you can round it. Usually if I can kind of avoid rounding something, because if I do 1 over 38, that gives me kind of a repeating decimal. I try to kind of keep it as the whole decimal in my calculator, so that's why I'm not actually converting it. This gives us a very large standard deviation, as most can expect in any casino game, because chances of you winning could be high, but also your chances of losing are also very, very high. 37.4967. One little just tip, especially if you're working with the calculator, if you want a fraction in your calculator, you can always just do alpha. You write it down. Alpha, and then y equals. And it should always be option number 1. It should look like n over d. And that will create a actual fraction setup for you versus just using parentheses and division. So sometimes that's a little bit nicer, especially when you're working with fractions within fractions within fractions. Now, I know it does not ask you to interpret, but I do kind of just want to review how to interpret again. It's always going to be if I were doing this many, many times. So if we were to repeat this experiment many times, the average number of spins until first win, always give us the context, would be approximately 38 spins. If we were to repeat this experiment many times, the average number of spins until first win, I always include the mean value in my interpretation of the standard deviation from the mean of 38 spins by about 37.4967 spins. And this kind of sentence stem is pretty much what we used when we were doing binomial distributions, because we do have interpretations for those on that notes paper as well. Okay, last topic. One thing that we've discussed before when we were doing normal distributions, and I know this isn't necessarily a normal distribution because it's skewed, but the same idea kind of carries over. If we get a probability, and if it is less than 5%, that is our threshold, we would consider it to be unusual. We would be surprised if it happened. We would disagree with what they say. We wouldn't support their claim. Basically, if it's smaller than that and it happens, that means something is wrong. Something is wrong with what they're telling me. So first question says, would you be surprised if Drew won on his first spin? So I'm going to go in and I'm going to calculate what is the probability of him winning on spin 1. So when I go in and I find this value, I really, in most cases, I'm just getting 1 out of 38. So formula-wise, you're just going to have 1 over 38. Now, if you want to overthink it and you want to do the entire calculator function, you can go in and still do Geomet PDF, where I have a probability 1 over 38 and I have an x value of 1. And both of those ways take us to the same exact decimal. They take us to 0.0263. And so what you're doing is you're taking 0.0263 and you're comparing it to 0.05. And so in our case, 0.02 is less than 0.05. So if it is less than 0.05, you find it unusual. You find it surprising. Whatever language they want to use for the question, you are in that place. So the probability Drew wins on first spin is approximately 2.63%. Again, very small. So it would be surprising if it happened. Now, just to kind of show you what it would look like in the other direction, would you be surprised if it took more than 13 spins of a roulette wheel until he won? So I'm going to go in and do the probability that X is greater than 13. Now, this is one where we're not actually including 13 in our inequality, because if they had said 13 or more, then I would. Or if they had said at least 13, then I would. But more than 13 does not include 13. So I'm going to actually use a complement where X is less than or equal to 13. Again, if you get stuck, write out a quick little number line, circle what you want, and then see what the last excluded value is. Last excluded value is 13. I'm going to go in anytime it's a less than. I'm not doing it by hand. Geomet, CDF, probability is 1 over 38. And in the actual function itself, you can type 1 over 38, 1 divided by 38, and your calculator will accept that, which is what I did. X value, the last included number I want is 13. And so I'm going to get 0.7070. Now, to interpret this, the probability that it takes more than 13 spins for Drew to win is approximately 70.7%. So if there's a 70% chance of something happening and it happens, you're not super shocked. If they say there's a 70% chance of rain and you walk outside and it's raining, you're not shocked about it. So it would not be surprising. So if you get questions that ask you, is it surprising, is it not surprising, this is kind of what they are leaning towards. Now, the last thing before we kind of go off and do math labs and all that stuff, I want you to take out your test review. You should have picked one up when you walked in the door today. And I'm going to get the question, I know. Is this going to be on the test? The first page, all of the notes, all of the formulas, is it there? And my answer is no, because it's never been on the test. But I will tell you, because I get that question quite often, on the back of that first page is what is actually going to be printed on your test. So that is the set of formulas that is on the AP formula chart. Most of what's on the front is there. The one thing that I would make sure that you know, and we noted this when we taught it back in before Thanksgiving, the very bottom table that talks about combining random variables together, that information is not on the formula chart that you get. So that is what you actually have to know going into your test next week. Most of the binomial, most of the geometric stuff is carried over into what College Board gives you, but what's going to be printed on your answer sheet is on that second page. So that is what you're going to have on your test. It will be there. I will probably remind you a bunch of times that it's going to be there, but not every single thing that's on the first page is on the exam. So make sure that when you're going in and you're studying, you're basing what you have to memorize on that. You don't have to really know a bunch about the binomial and geometric, but the combining random variables, you do. So